Welcome back to Daily Dose of Space, your place for the biggest discoveries, the strangest mysteries, and everything happening above our heads. Today, we're looking at something truly rare. NASA has just captured the clearest images ever of an interstellar comet, a fragment of another solar system drifting through ours. This is only the third interstellar object humans have ever seen, and what these new images show is shocking. Fractures, scars, and chemistry that tell the story of a world completely unlike our own. So let's break down exactly what NASA found, what makes 3I Atlas so unusual, and why this might be our best chance in decades to study an object from another star. What did JWST actually saw? The James Webb Space Telescope was pointed at a young star surrounded by a protoplanetary disk, a swirling, dusty, chaotic structure where planets are still forming. These systems are usually rich in simple molecules like water vapor, carbon monoxide, and basic hydrocarbons. But in the new JWST spectra, scientists identified distinct signatures of something more complex: polycyclic aromatic hydrocarbons, often called PAHs. PAHs aren't simple molecules. They contain interconnected rings of carbon atoms, and they're considered an early step toward even more complex organic chemistry. Usually, PAHs are found in older regions of space where dust has been exposed to enough ultraviolet radiation to trigger complex reactions. Young disks, on the other hand, are messy, dense, and full of radiation-blocking dust. Most models predicted PAHs shouldn't show up until later, after the disk evolves and clears out. Yet JWST is now showing the opposite. They might form early, or survive conditions we didn't expect them to survive. Why this breaks old models? Planet-forming disks typically heat up on the inside and cool down on the outside. Carbon molecules are thought to form farther out, where temperatures are lower. Inside regions where rocky planets form, the terrestrial zone, temperatures should destroy large molecules. But the JWST detection was made inside the terrestrial zone. That means these complex molecules are surviving conditions that should, on paper, break them apart. This challenges a major assumption about how planets like Earth get their carbon. Traditionally, scientists believed carbon-rich comets and asteroids delivered it long after Earth formed. But JWST's new observations suggest a different possibility. The raw materials might already exist inside the early disk, right where rocky planets are being assembled. If that's true, then Earth, and worlds like it, might start out with far more organic material than we previously believed. What this means for planet formation. If complex carbon forms early, it changes the story of how planets take shape. A disk rich in PAHs can feed material to growing planets as they sweep through the dust. Some of it gets baked, some trapped in rocks, and some might even become part of early atmospheres. What's more interesting is how early this is happening. This system is only a few million years old. For comparison, Earth didn't stabilize into a fully formed planet until nearly 100 million years after the solar system began. If these molecules are present so early in other young stars, then the seeds of habitability might be universal, appearing right at the beginning of a system's life. Are these molecules linked to life? PAHs are not alive. They are not biological, but they are a fundamental stepping stone in prebiotic chemistry, the stage before biology. PAHs can absorb UV radiation and break into smaller fragments that react to form amino acids or more advanced organic molecules. In laboratory experiments, PAHs exposed to the right conditions produce chemical products relevant to life's earliest chemistry. So, this discovery doesn't suggest life in a young disk. What it does suggest is that nature wastes no time in building the ingredients that life might eventually use. It raises new questions about how common chemically rich environments are around young stars. And because this is the first time we've seen molecules like this in such a young region, it opens the door to many more discoveries. What astronomers expect next? This discovery is just the beginning. JWST's instruments will now target dozens of young disks to see whether PAHs appear everywhere or whether the system is unusual. If they turn out to be common, it will rewrite our models of disk chemistry. It might also help explain why carbon is so abundant in meteorites from our own early solar system. We'll also get better insight into how these molecules survive. Perhaps they're shielded by dense grains of dust. Perhaps they form faster than they break down. Or maybe energy from the young star triggers chemical reactions we still don't understand. Either way, this is one of those discoveries that seems small, but carries enormous implications for planetary science, and potentially for the long-term question of how life gets started in the universe.